So, following with the topic of energy, you're going to start today with the basics of oil and gas. Obviously, this is not a non-renewable energy, but it's a classical way to power our modern society, and it's going to be with us for a few years still. And it's quite interesting the view from Latin America. So that's what we're going to do today. First, start with the basics, and then go into the particulars of oil and gas in Latin America. So, if we look into a general consumption of energy by energy source, we see here is an evolution. Can actually see here different graphics: petroleum and other liquids, renewables, which are at the present level right here. Obviously, we see here to 2020 right in this moment, and in future perspectives, you're going to see renewables increasingly more and more important. We see natural gas, coal, which is declining, and nuclear that more or less keeps in the same level of production. So the projections we see here, this is all coming from the Department of Energy, which is a very reliable source. You can actually access by using this direction in the internet. And see, in 2020 we see here the evolution is going renewables, that in about 30 years you're going to have an increase close to 50%. Coal is decreasing, not really by much, and not as much as we want, but it's decreasing. Petroleum and other liquids still more or less constant. Natural gas is about the same, and nuclear is also about the same. So we see here in this projection to the future, we see here a rather large increase in renewables, decreasing in coal, and obviously decreasing in petroleum and other liquids. Natural gas and nuclear are more or less in the same level. So those are the projections, obviously, but things are changing rather quickly. What we see here? You see, 2010, 2020, and here is a bump. This bump happens very much everywhere in the consumption, and it's obviously due to the pandemic influence in the use of energy in the whole world. So that's something quite interesting that happens a while ago, 2 years ago, and we're still recovering. And we see here the recovery seems to be more or less in the same way. So these lines and natural gas almost not even having a dent in there, because natural gas is much more used to generation of electricity than anything else, while petroleum gas in particular is much more used for transportation and was greatly affected by the pandemic event. So that's the tendency we see in the next 30 years. Electricity generation by the different kinds of fuel in trillion kilowatt hours in 2007 happened to be more or less in this value here. Fossil fuels, 62%, and then we have nuclear, dumped together with hydroelectric, wind, and solar, 35%, and some others which are not even close to 3%. By 2020, we probably going to be seeing a big change in here. We see nuclear, wind, gas, hydroelectricity much more important. Oil is still decreasing. So this is what we expect for 2021. Now, talking about oil, hydrocarbons in general, I should say, the origin of hydrocarbons is in living things. Plankton in general, including phyto and zooplankton, obviously. By degradation through geological processes, we see this plankton or this organic matter changing into hydrocarbons. In general, we may say the majority of this biomass is being produced by small in size organisms living in the water. In general, there are some other exceptions, but in general, that's the main process. When they die, they go to the bottom and maybe get into the sediment, covered by sediment. So it happens to be buried rather quickly. The preservation is better. Over the years, through geological processes, we start to increase the heat and the pressure in these rocks, and that evolved the biomass into hydrocarbons. You're going to see we receive different names depending on the process of transformation. So we do have, in general, these two, this biomass can be discriminated in two main elements due to the different properties: oil and gas. These two hydrocarbons tend to migrate towards the surface when there is a chance to do so. We may have accumulation in something we call traps, geological traps, so that's where we normally look for those traps to catch an accumulation of hydrocarbons in those fields. So, in general, then as a summary, we see biomass accumulating over a long time and process over a long time to produce what we see today as a hydrocarbon we use for producing energy today. So accumulation of organic matter, which is called sapropel actually. Sapropel accumulate, and then through temperature we do have a quick transformation in very low temperature, about 80 Celsius, into something called kerogen. The sediments are actually accumulated on top, forming what we normally call the source rock. By increasing temperature and pressure, this is just due to geological processes. The deeper we go, the higher is the temperature and also the higher is the pressure. So in that way, kerogen, it can be transformed into hydrocarbons. So we increase pressure, we increase temperature, and then biomass, it goes into kerogen, and eventually into hydrocarbons. So that's a well-known process. And once we have the hydrocarbons produced, migration is something may happen and accumulate in a particular place we like to call traps. It happens sometimes that the hydrocarbons are not preserved or are preserved depending on the condition. If the migration happens into an area that is exposed to the outside, those hydrocarbons may oxidize and be lost for the future. So overheating also is not really good. So if we do overheat the kerogen, actually we may cook too much the kerogen and produce a degradation of the hydrocarbons, so there's nothing left. So we see some of these steps. This is a video that you should see. It won't take more than about 2 minutes because it's coming from an institutional education from New Zealand, and it's summarizing the whole thing. I'll let you see it.
Dead plankton sinks to the ocean floor and gets deposited. The plankton is mixed with fine mud, clay. The resulting sediment made of the plankton, mud and anaerobic bacteria is now called sapropel. Sapropel is being buried by younger sediments, which increases the pressure and temperature of the sapropel layer. At about 50 degrees centigrade, corresponding to 1 to 2 kilometres of burial, the sapropel is converted into kerogen through anaerobic bacteria and chemical processes. The sediment layers may be folded as a result of tectonic movements in the basin. More sediments fall on top, increasing the pressure and temperature on the kerogen. At 80 to 120 degrees centigrade, or about 3 to 5 kilometres of burial, the conversion of kerogen into liquid petroleum occurs. The oil migrates out of the kerogen into sandstone reservoirs. These act as storage beds. Between 120 to 150 degrees centigrade, natural gas forms and also migrates from the kerogen into the sandstone reservoir. In some sedimentary basins, additional salty water might migrate into the sandstone reservoir and underlie the oil. An oil or gas field forms when the liquid or gas moves through the pores and spaces of permeable rock and collects within the pore spaces under an impermeable trap.
I hope you enjoy it. In general, what is summarized in that video is what we see here. This is a little more technical graphic, and representing in this direction depth in feet, and in this direction temperature in Celsius. So remember, Celsius, if we go 100 Celsius, that's actually boiling point of water. So just to have an idea. So if we start with kerogen in a temperature which is below 60 Celsius and a pressure equivalent to about 5,000 feet, we do have kerogen. As soon as we go below, higher than 60 degrees and a pressure equivalent to 60,000 feet or so, we may start to separate from the kerogen the hydrocarbons, which is what? Oil and gas. So this is the place where we want to be, where we want our source to go through. No more than 120 Celsius, and got to be a little higher than 60 degrees Celsius. So this is what is called the oil window. If we happen to go over 120 Celsius, close to 140, we do see more gas than oil. In fact, it's called wet gas, because it's coming with some hydrocarbon, but not much. Now, if we go deeper than that and higher temperature, 140, 20,000 feet, no more oil, just gas. That's the only thing is left. So is this convenient? Well, it's not, but we get what we get. When we drill and look into different conditions, we find out whatever happens to be there, but do you know, according to this, that the best place to look for something in normal conditions is between 6,000 feet and no deeper than 15,000 feet to find the optimal condition. Now, if you go deeper, may actually get gas with some hydrocarbons, but not much else. Now, deeper than that, only gas. So, temperature increase, we start to mature the organic matter. The kerogen goes into hydrocarbon, gas, and oil. Most oil is produced between those temperatures. We just mentioned that. It's something called the oil window. Also, it's called the kitchen sometimes in the jargon of the oil explorers. Did I just say that? Now, once we have the oil, and this is something changing, the concept is changing, hydrocarbon forming something we call the source rock. That's the place where it accumulates and over time mature and become a hydrocarbon that migrates, go into a place where it can accumulate. Nowadays we are actually searching for the rock itself, for the source rock itself, and making it produce. So, most of the time in the classical way, hydrocarbons migrate and go into something we call the reservoir, happens to be a rock, that got enough porosity or fractures where the oil can actually be stored for some time and become a significant amount in volume. So petroleum migrates, but not just as petroleum. It's a mixture of oil, gas, and also water. So those three things go together away from the source and to the reservoir. And obviously in the reservoir they separate according to density. So for example here, it's a little busy, but it can really be seen quickly. So this is the source rock right here. That's the place where the organic matter accumulates over the time of sedimentation, where immature after the temperature and pressure are enough. And then we present the source in here with a way to migrate from this place in here to another place where it can accumulate. So this is the trap. And the trap normally is produced by a fault, like in this one, in this case. And there, when the rock do have the proper conditions, this is called a reservoir rock. The reservoir rock is more than anything a rock full of pores or fractures. You got enough empty space, it can hold in there the three different products of the maturation. So we see here gas on top, like here, this color is not proper, gas in here, and then we have oil, and finally water, just by density. You know, you put all this together in a container, you're going to see the gas goes in top, then oil, and then water. So, another classical way is the anticlinal theory. It's just a deformation. This is the typical deformation that we call anticline. And see here, we do have a rock. This particular rock is the proper one with a lot of porosity. And there we have the typical accumulation of water, oil, and gas. So we can actually drill in here, reaching the proper place to extract the oil. Same thing here. Some examples. Here we have the classical anticlinal trap in Prudhoe Bay. It's in the north slope of Alaska. An important reservoir over the years. And we see here a really large migration from the Brooks Range all the way to the Beaufort Sea in the north here. So all in all, this is in the order of several hundred kilometers to the north. And the migration happens all the way from here into this part where the accumulation is, where the reservoir is placed. Now, for a reservoir rock, got to be a place where the oil and gas got a volume to fill. So that requires porosity. So porosity is the space in between the grains. So we have here grains, an empty space in between the grains. This is the pore area. Now, porosity is not just really necessary. We need also communication between the pores. In that way, the liquids or the fluids, more properly, it can move from one place to the other. Because if we have a pore here and that pore is closed, it won't really let anything in or out. So what we really look for is permeability. The concepts are similar in a way, but not always. No? Porosity is the amount of spaces in a rock. Permeability is the communication between those pores. So those two properties can be measured. They are measured in order to know how good your reservoir is. So, requirement for traps, this is obviously something very much a preoccupation of engineers. The traps are normally formed by porous rocks, sealed by impermeable rocks on top and in the bottom. That way we have a perfect package where things go in and stay there. We do have several kinds of traps. We just mentioned the anticline trap, stratigraphic rock layers forming a particular length of porous rock, or we may actually have a fault communication. Anyway, try to have in here most of them. See, this is the anticlinal structure, and it's a little out of phase. This is the anticlinal, that's the trap. Here we have a fault blocking this migration here, producing a trap for a hydrocarbon here. In this case, it's just gas, doesn't really matter, but it's gas, can be gas and oil. And here we have a change in the nature of the rock. This rock that used to be very porous in here is actually porous in here, changes. And it's no longer so permeable, so it's trapping the oil in that respect. So all that is, and many other combinations are possible to produce good accumulation of this oil, hydrocarbons, I should say, oil and gas, in different places, and making a viable, economical way to produce oil. Because all this got to do with money, obviously, as you can realize. Some other forms, same thing, really, just another set of the same kind of examples. So to produce oil, what we normally do is drill into the reservoir, and got to be in the place where we have oil, and that thing will produce oil out spontaneously just by pressure. When they happen to have a good reservoir of gas on top, that gas can actually pressure and helps into flowing the oil out of the well. When that happens, it's a natural surging oil, gas oil, but many times we're going to have to help producing some kind of pumping down into the bottom of the well. Obviously, you don't want to drill in here, because if we do, we're going to produce only water, and it's not really something we want. And we don't want to do this either, because if we take the gas out, we're going to deplete the pressure of the reservoir. So the best thing to do is first this one in here, and then eventually, when the oil is being depleted, may actually go into number 2. Number 3, obviously, nobody wants water, so not this water in particular. It happens to be very salty in any case. So now, inside the basis of oil, of hydrocarbon production, we see different kinds of oil. And we normally try to associate oil with just black material, very sticky and all that, but there are many different kinds of oil depending where we get it. Typical oil coming from Texas, what we call the East Texas Light Texas crude here, 1 barrel, which is about 42 gallons. This is a very important unit, very much when we talk about barrels, they're always 42 gallons. We can extract from this particular oil this amount of gasoline, about 20 gallons of gasoline, fuel oil 9.2, jet fuel 4.1, asphalt 2.3, kerosene just a tiny bit, and then heavier elements, lubricants, petrochemicals, other things. This is very different depending on the kind of oil we deal with. Light Texas crude is a really good oil. In that respect, it's also having a different price. The value is different depending on how many of the elements we want are present there. There are some oils which are very rich in asphalt, and obviously that thing is not always what we want. Some oils are very rich also in toxic components like hydrogen sulfide. This is something that nobody wants to deal with because it's extremely poisonous. It's a really bad thing to deal with. Now, the other thing we have to do in these basics of oil is realizing that getting the oil is not really easy at all. In particular, today we go through something like this. A drilling rig is necessary to break through the rocks. Normally, the breaking through the rocks is done by the bit in here, which is rotating. It's a rotatory bit, and the rotation happens at the same time we are injecting a very high pressure liquid that is coming from this container here. That pressure, that liquid under pressure is injected and is helping to break the rock in the way down. Plus the pressure of the pipe that is going wading on the rock and breaking the rock in pieces, very tiny pieces that are actually recovered by the fluid coming back into the pooling here. So that's normally the way it happens. It's a very involved operation. See here all the many different things. We have a large number of people working in there, especially today where we have a different technology using after the drilling is done. Is a posterior stage we call fracturing or fracking, more well known today, where the breaking up of the rock is necessary. So that involves a little more. Well, here are some of the details. See, this is the main tool that is breaking the rock. This is the typical rock bit. We have sometimes, as a necessity to obtain a central part of the rock for analysis, and that central part coming through here and is recovered, and is what we normally call the core. That core is very valuable for understanding the geology, and it's actually very expensive too, because you have to change all the pipes in here in order to change the tool, and then drill as much as necessary, recover the core, and change it back to the normal bit. So done sometimes, but not always. Normally the material we get out of the well is just tiny bits like this that we call cuttings. And so cuttings are a continuous sampling of the rocks that have been drilled in this process. So this is a technology already more than 120 years or so. So we know quite well how to drill using this. The cost of this is always changing, but it's about $30,000 per day in an onshore situation. Now, if you do it offshore, it's way more expensive, or $500,000 per day, depending where you are, obviously. These numbers are very general and changing in different places, different conditions, depending how far you are from shore, depending how far you are from populations and places like that. So every basin, every field got different expenses. These are just to give us an idea how things work. In offshore, on top of being more expensive, each one of these drilling rigs happen to be either floating, semi-floating, or like this one in here, anchored into the bottom of the sea. This place takes a lot of investment to be put in the area. So drilling is not just one time. It happens to be drilling bidirectional drilling into many different areas. Sometimes 10 or 20 wells can be drilled in the same place. And as the same thing, all these wells go producing into the same area, which is actually quite well for collecting. So very expensive, as you can imagine. Once the pressure in the reservoir goes off, see, the pressure in the gas is not really enough to push the oil out, we do have to put in here a pump down there. And that pump is really a pump, happens to be the same size of the pipe, and it's activated by a bar that goes in and out, pushing the oil out from the bottom up. Much more expensive, obviously, as you can say, but you know, when the price of the oil is good enough, it can be done. Sometimes we use an extra push, like here. We have a well here that is pushing by injecting water and moving the oil into the area where it's captured. So these are secondary recovery that happens to be used when the economics are making sense. Obviously, if this is not really making you enough profit, don't do it. That's what happened. And many times these things are working in a particular time, and then when the economics of the oil business are making the cost of the oil go up and down, well, these things are going working or not working depending of the profit, obviously. Now, who is using the most oil? Well, interestingly enough, since it's an expensive commodity, we see the 20 richest countries are the ones that consume the most oil. 80% of the natural gas, 65% of the oil, and 50% of coal. Just two countries, US and Canada, are using 25% of all the energy. Now, if we look into this map produced by BP in 2021, we see here the oil consumption per capita is quite high, obviously. Highest in Canada, Australia, Saudi Arabia, what else? And then we go into United States, Norway, Europe more or less in general, and Russia. And then we have less consumption, and we see it's a correlation between consumption and GDP or GNP, whatever you're going to use it. But see here in this graphic, see a quick correlation. See the United Arab Emirates, and we see Kuwait somewhere here, well, anyway, here, United States. And then we see here China is obviously out of reality here. This is from 1999. China is moving along into the proper correlation. Now, a preoccupation that happened to be quite large a few years ago, 1970s, all the way to the 2000s, is how long we're going to have oil and gas, hydrocarbons in general, when we're going to start running out. Well, see, the projection was like this. According to Hubert, in a famous paper about 2005 or so, you start to see decline. And for 2050, it were not really any oil left. Well, that was the technology in those days, and we see here different parts of the world according to the production and all that. But we have new technology, and this is actually changing the game. This new technology is changing the perspective, it's changing the availability of new reserves. So things are now the same way. This technology is what we call fracking, or fracturing and injecting water. So what happens here is we have a drilling. Normally that drilling can be directional and going horizontal, following the source rock. And once the well is completed to the desire of the engineers, they pressurize the well, making the rock break in a particular way. Once the rock is broken, an injection of a particular kind of support happens and goes into the fracture and hold the fractures open. So this is the way we can produce more from rocks that we couldn't before. Problems? Well, there are many problems with this. One of the main problems is we do have water leakage from that fracture into places we don't want to be, particularly going into the water table. We may have losing some of the gas out of the place. That's something we don't want to. But obviously we are accessing resources that were not really available before. This is expensive, obviously. Not just drilling the well, not just using new tools to make the well go horizontal in different directions, fracturing the rock, using support, all that is adding up, making this much more expensive. And all in all, today, a premium well cost, finish and producing, is $6.6 to close to $1.5 million. So it's much more expensive, but it's producing. Now, this is a new player in this new way to observe reserves, and it's what we normally call shale basins. Now, right here we talk about gas, but gas is also producing with some oil always. So we see now players that were not really there before. You see China. China do have the most reserve of gas in the world now. From being without gas, now one of the potentially larger producers of gas, and this is in trillion cubic meters. Followed by US. This is actually coming from 2020. Then we have Argentina. That wasn't really. Today Argentina is lacking gas. We got to develop the field here, the so-called Vaca Muerta. They haven't really done it yet because it's expensive, as we mentioned. Every well requires at least an investment of 5 to 8 or even more $1 million. So these things are there. So we do have more reserves. So we're not really running out of oil. In fact, we see here, look at this. Shale gas is coming with a very large volume of possibly energy producing material. So shale gas, tight gas, which is quite similar in a way, we don't really go into that. And see, it's a very important resource going to be developed, not yet. Right now we are here, about this point in here. But it's going to be even more through the years. So the oil reserves going from 2000, 2010, 2020 is getting larger. So this, the end of the cheap oil is not really cheap still, but it's proven to be increasing over time. So what we see here today in 2020 is about 1,732.4 thousand million barrels of oil reserves. Most of it is obviously Middle East, but we have now some other players, South and Central America here, that used to be 7.4, now is 18.7 thousand million barrels. So this new technology is opening a new window in the energy war. But see, the reserves, again, it's the same thing, but now in a different kind of graphic. We see here South and Central America do have a large volume of reserves. Particularly the heavy weights in here are Venezuela for oil, one of the major reserves in the world. And if we talk about gas, Argentina is also contributing to this. So big changes in there. Interestingly enough is to see oil reserve to production, what's called RP ratios. You see the major production is, it happens to be in the Middle East right now, but in potential we have other places, South and Central America, coming along quite well. Major oil trade movements, it's an important part, in particular for oil coming from the Saudi Arabia that is going all over the world. The United States is not really depending much of long distance transport like it used to be. Now the major seller of oil to the United States happen to be Canada, and in some part Mexico and Venezuela used to be. I think it's changing now, but the U.S. happen to be mostly independent of the rest of the world. Now this is something may be interesting for everybody, and it's interesting because it's making a correlation between historical events, and the price of oil. This is $120, $140 per barrel, obviously, zero here. And we see here a big oscillation. This number in here, this is this color in here is current price. So we have a large increase of price here, 1970s. This is the peak. It happened in 73. So let's see here more or less we were in this point in the 2020. And if we look a little closer, see what happened. Spring 2020, oil went negative. Essentially because nobody was using oil due to the pandemic, the storage capacity was not there, so people were actually paying for somebody taking the money out, the oil out. So now it recovered and is more or less in this place than December 2020, and you know, today the price is very high. 2020 production, and this is the projection of what is going to happen by 2040. So we see here the pandemic effect, and 3 different scenarios. According to this, is coming from BP. The source is open; everybody can access. Business as usual, probably going to be picking over this, pointing here, and then decreasing. If we do a quick change into renewable energy, we're going to see a rapid decrease from this point on. And if we try to go into net zero by 2040, this is the way we should be. So obviously, we are probably going to go in this way. Business as usual. It tends to be the tendency in all the things. So different forecasts depending on who is seeing the reality into the future. And see here by Rystad, by Bloomberg, the OPEC. And see this is the demand of oil 2040, 115 million barrels. So see the peak in here will be 2035, 28, 35, according to this one in here, according to OPEC, 2040. And then will decline with the present reserves. So what we do? Well, we do have, again, technology saving us, and this is the way it should be. So what we see here now, the consumption of fuel for transportation in particular, that's one of the main indications here. We're going to see a replacement of the internal combustion engine by electric plug-in and fuel cell in excess of 50%. So by 2040, we're going to have only this part in here, this transportation, this powering our cars by probably about 30% or even less. So less gas to be used. What we put in here as a title, the sunshine, it will be the new oil. Fuel and electricity generation used to be the same thing. Now we have another way to do. So sunlight generation is going to be the main way, together with wind generation and such. We do have already a big advance in this. We used to think about 50 years for electric cars to have some impact, but it's already happening. So transportation will be electrified. Solar power is actually the cheapest way to produce energy in most of the world. Obviously, the countries that need the most energy will be the most beneficiated by this, because they happen to be in the place where the most sunlight is. Now the countries in the high latitude will be less benefited, but you know, there's always a way. So electric vehicles are the way to do transportation. So sunshine is the new oil, and that's that's the way we are decreasing the usage of fossil fuels in the near future. Right. So next lecture we'll go over Latin America oil. In particular, I'm going to talk about different countries. It's going to be somewhat an introduction to countries which are net producers of oil, in particular Venezuela. And then a new kid in the block is Brazil. We happen to be producing oil like never did before. Okay? All right, that's it. Thank you very much.